For question 11, we're also going to be looking for the max and min with Lagrange multipliers, and we see that over here, this is indeed a closed bounded region, so we can apply EVT, but it's not going to make much of a difference. It's just that we're now looking for the absolute max and min. So let's go ahead, and since this is a function of 3 variables, we'll adjust our constraint g function as according so. And we would get straight into our Lagrange multiplying. So let's set up our functions. For f of x, it's going to be equal to 2x, which is going to be lambda g of x, which is going to be lambda 4x cubed. And we're going to go ahead and repeat that for all of our other derivatives. And if we rewrite that over here, it's going to mean 2x equals to 4 lambda x cubed to y equals 4 lambda y cubed, and 2z equals 4 lambda z cubed. Of course, never forget the original constraint we had. And let's look at things. So we can, for the top function, top equation, it looks like we can take out 2 of x. So it's going to be 2 lambda squared is equal to 0. And we can apply that for all of them. 2 lambda y squared equals 0, and 2z means 1 minus 2 lambda z squared will equal to 0. Now what this means is that x can be 0, and we'll have a bunch of scenarios when that is the case. Y can be 0, and z can be 0, but not all of them can be 0 at once based on this. And we do realize that our constraints and for our original function, all these variables, nothing are interchangeable. If we move x and y over, it's not going to change. Z of x, z and y, z of x, none of them are going to change. So we call these symmetric, both our constraints and our function. And because we know both our functions are symmetric, what we can do is basically just assume, hey, I'm going to apply a situation where, let's say, x is 0, and that's going to be the exact same situation whenever I pick y is 0 or z is 0, and for all the other cases. So what that basically means is that I'm going to set, let's try a place where 1, 0. And then I'm going to do a case where there's 2 zeros. And because there's no case with 3 zeros, we already saw that that's not going to happen. I'm going to go over ahead and go to say there's a case with no zeros. So let's see here. What if x was 0 and that was the only 0? Well, that would mean x is 0, but y has to be, or 2 lambda y squared has to be 1, which means that lambda y squared is 1/2, and that lambda is going to be, or rather, y squared is going to be 1 over 2 lambda. And that's going to be the same for z. And we can plug this in to the constraint, original constraint, by squaring our two values. So this means y squared, y to the power 4 is going to look something like this, and z to the power 4 is also going to look something exactly the same. And since x is 0, 0 plus 2 over 4 pi lambda squared, we can get rid of this 2, is going to be 1. And so what we know is that 1/2 is equal to lambda squared. Lambda can either be plus or minus, root 2. And that carries over to our y and z. So y squared is 1 over 2 root 2, which basically is root 2 plus minus. And because it can't be plus minus because y is squared, move that to this. And the same is going to happen for z, which basically means that y and z are both plus minus 1 over 2 root 4, or 4 root 2, whatever you like to pronounce this. For two zeros, which means that x and y are 0, that's a little bit more of a simple case because we again applied it to our original constraints. That just means that z to the power 4 is going to be 1, so z is either plus or minus 1. And we don't need to look for any lambdas, that's just going to be it. And for our zero section, which is going to be the most difficult, it is going to look something like the original. So we already know that our x, y, and z are all going to look, squared, are all going to look something like this, which means that all of them to the power 4 is going to look something like this. And because there's 3 of them now, 3 over 4 lambda squared is going to be 1. 3 equals 4 lambda squared. Lambda squared equals 3 over 4. Lambda is going to be plus or minus root 3 over 4. Let me just write like that for now. So we can bring this back to each of the squares. And because it's a square, we know that this can be minus. So 2 times root 3 over 2, get rid of the 2. It's going to be 1 over root 3. Because these are square, x, y, and z are each going to be the 4th root of 3. So we have 3 cases, each represented with 1, 0, 2, 0, and 3, 0. And let's plug into our original function of x, y, z is equal to x squared, y squared, and z squared. So our first function with 1, 0 came out to this, 0 plus 1 over 2 plus root 2, 1 over root 2. That is just going to equal to root 2. For our situation with 2 zeros, it was just 0 plus 1, which will equal to 1. And for our case with no zeros, like this, it's going to be 1 over root 3 plus 1 over root 3 plus 1 over root 3, which again will equal to root 3. So our minimum, absolute in this case, is root 2, and our absolute minimum is 1, and our absolute maximum is root 3. Of course, we can look for all the different scenarios when x is 0 and y and r not, and y is 0 and x and 0 are not, but in this case,